Okay, yes, so just 1 second. Do you want to appear in the video, or would you like kind of not to appear?
Nah, it's the same for me.
Yeah?
It's okay if I appear.
Yeah. Okay. All right. Then you can start if you want. So can you share?
Yeah.
Yeah. Okay.
Okay. Okay, there it is. Right. Yeah. Okay. Well, so today I'll talk about affine connections. That is a way of generalizing the idea of the directional derivative of a vector field in the direction of another vector field to an arbitrary manifold. So yeah. Then we can consider a manifold M and an open set U as subset of M, and two vector fields X and Y defining U. And we would like to measure the way Y changes in the direction of X when M is the real n space. We can do this using directional derivatives that are defined by this limit. But well, in an arbitrary manifold, this limit obviously does not make sense because the reason for which one can do this addition is that, well, Rn has the structure of a vector space, right? Moreover, we can also think about this addition being possible because there is a canonical identification between tangent spaces for different points in Rn, which doesn't happen in an arbitrary manifold. So it is unclear how to generalize this notion to an abstract manifold in a convenient way. And well, if we think about this particular limit, a way of doing it would be to construct something that allows us to give an isomorphism between different tangent spaces, right? And that is what the concept of parallel transport along a curve allows us to do. But well, the way I'll do it, we will actually solve the problem earlier, because to introduce parallel transport, we introduce affine connections, and affine connections are essentially a way of differentiating one vector in the direction of another. Yeah, one vector field in the direction of another vector field. Okay, so we'll first talk about connections. And yeah, so an affine connection is an R bilinear map, or defined on a manifold, is an R bilinear map that goes from the space of vector fields times the space of vector fields to the space of vector fields, right? And such that the following two conditions hold. The first one is that the map, well, what this is telling us is that the map is not only R bilinear like in the first entry, but also C infinite bilinear, right? That it takes away functions. And the second property tells us that the map in the second entry is not exactly C infinite bilinear, but that it has a special of a type of Leibniz rule, right? Or product rule. And well, these properties are natural because one is thinking about the properties that the directional derivative has. Okay, now Yeah, so the directional derivative is, in a sense, local. Okay, so to calculate the directional derivative, it is enough to know the y in a neighborhood of a point, right? If we have a globally defined vector field y, it is enough to know that globally defined vector field in a neighborhood of the point where you are calculating the directional derivative. And moreover, it is enough to know the vector field in which direction you are differentiating in that point. Sorry, I don't know what happened. Give me a second. Okay. Okay, what I'm saying is that you need to know x in the point only pointwise and y in a neighborhood of p. So we'll see that this is also true for an arbitrary affine connection. I mean that the value of the connection for, if we fix x, is determined by knowing y in a neighborhood of the point where we want to calculate the connection, and the value of the connection if we fix y is determined if we fix a value for x at the point. Okay. So now, yeah, the first part, we want M once again to be a smooth manifold. We want Y to be a connection on M. Sorry, here I should have put nabla, not Y. And for every open subset U of M, for every vector field Y, a smooth vector field, of course, if Y is identically 0 on U, then evaluating the connection in the direction of X, yeah, evaluating or differentiating Y in the direction of X is 0 for all smooth vector fields. So yeah, and by linearity, what this is telling us is that if two vector fields agree in a neighborhood of a point, then the evaluations or their differentiation at their direction of X will also coincide. Now, so suppose Y is a smooth vector field that is identically 0 on a neighborhood of a point, on a neighborhood U of a point P, and we can choose a bound function that is a infinite function which has support in the neighborhood that we are interested, and such that it has value 1 at the point P. And then since Y vanishes on U, then the product of Y with phi vanishes in all of them. Yeah, it's 0 as a vector field. So when we calculate, when we differentiate this vector field in the direction of X, we can do this, right? And this one is 0, and that's the same as 0 times the vector field, which by the properties of bilinearity, one can take the 0 away, and so that will be 0, right? And then the product rule guarantees that 0 is equal to this expression here. And when we evaluate at the particular point P, since Y at P is 0, this term goes away, and phi at P is 1. So the directional derivative of Y in the direction of X is also 0. Okay, that's
so, Carlos, I have a doubt. So what was the meaning of a vector field like X being evaluated on phi? How does it act? I don't recall it.
Okay, so
sorry, can you repeat the question? Sorry, I didn't understand.
Yeah, my question is, what's the meaning of the symbol on equation 6, the first summand, x evaluated or acting on phi? I don't recall the meaning of that action.
yeah, okay, so tangent vectors can be seen as something called I forgot the name.
Like derivations or what?
Derivations, yeah, sorry. So derivations are functions that go from C-infinite functions to C-infinite functions, right? And that fulfill certain properties, that is R linearity and a Leibniz rule. Okay, so the way a vector field acts at a function is that you evaluate the vector field at the particular point where you want it to act, and then that tangent vector acts at the function as a derivation. Okay.
Okay, thank you. So, okay.
Just can I add something?
Yeah, sure.
Yeah. So I mean, wouldn't it be kind of a bit simpler to say, you know, if you have a vector field at each point, you can take, you know, at each point P, you can take the derivative in the direction of x of that point of any C-infinity function, right? I mean, kind of given a vector field, since at any point you have a tangent vector, you can take the directional derivative of any C-infinity function. And then x of P is the C-infinity function given by at each point, you take the directional derivative of phi at the direction given by x at that point.
Yeah,
Right. I mean, it's the same, right?
Yeah. The thing is that it is hard to. I mean, it's a little bit hard for me to think of a coordinate-free representation or a coordinate-free meaning to directional derivatives, right?
Okay.
So yeah, that's why I always think about derivations. But yeah, that's actually the idea, or that's what one is trying to generalize when one defines derivation is directional derivatives. Yeah, that's totally true.
Thank you.
Mm-hmm. Okay, so now, well, we want to see that if we have a fixed vector field theta, to calculate its directional derivative, it is enough to know the value of the vector field that gives the direction in a single point, right? And well, if we know this, then it is perfectly fine to write something like this, right? To write the directional derivative of the vector field theta in the direction u at a point P. Okay. I mean, we would simply take a vector field that has the value u at P and evaluate the connection. Okay. So by linearity,
just one little thing. So in the previous slide, yeah. So I mean, I agree that from that we can conclude that the expression nabla u of z evaluated in P makes sense. But just kind of one needs a little extra step that if you give one tangent vector at a point, that you can make it part of a vector field, right?
Yeah, but that's that.
I mean, is it completely just trivial?
No, it isn't. You are right.
I guess you can take kind of a chart around the point P, and then in that chart you can you can make U part of a vector field there, and then with a bump function, you can make it 0 outside that neighborhood, and then you get your vector field, I guess, right?
Yeah, you are right. It is not trivial. I know it can be done, but I hadn't think about it. But it is also not so hard, because probably one should be able to reduce it to a problem in differential equations, right?
Right. No, but I think it's what I said solves it, I think. With yeah, I mean, yeah, like again, take a chart around the point P, and then take in using the chart in that neighborhood, you can extend the vector U to the kind of to the constant to a sort of constant vector field in that small neighborhood, and then with a bump function, you can extend this so that it is 0 outside the neighborhood. It's fine. I don't want to.
Sure.
I don't want to.
Yeah.
Yeah, we can discuss this later.
Yeah.
I don't want to kind of get you out of rate.
Yeah. Okay. So by linearity, once again, it suffices to prove that the directional derivative of zeta in the direction of x is 0 if we know that x evaluated at the point B is 0. So we can choose local coordinates for M around B such that x has this representation in those local coordinates. Oh yeah. In the future, I won't write it. I won't write the local vector fields like this, like partial over partial xi, because it is really cumbersome, notationally cumbersome. So I'll just write partial I for the vector fields induced by the local coordinates. Okay, and since we are assuming that the vector field is 0 at the point P, then the smooth functions xi should be 0 at the point P. Now, then for every y for every smooth vector field y, we have the following, right? Just using the properties of connections, and we have this, and since each xi at P is 0, then this whole thing is 0, and that's what we wanted to prove. So yeah, it is quite simple. And now, so we know now that a connection from the first proposition, we know something that we are actually using here, that the restriction of that a connection can be restricted to an open set of a manifold, right? And that it will still be a connection, and that the connection in the restricted open set will be the same as the connection in the whole manifold for the points of the restriction. And that we are actually using that here because we are working with a restricted connection, right? So that this idea of the coordinate vector fields makes sense because this representation isn't global. So we need to work with the restriction. Okay. Now, if we fixed a system of local coordinates, I mean, if we have a connection and we fix a system of local coordinates, since the local coordinates induce a local basis for the tangent spaces, then we know that evaluating the connection at these vector fields must have an expression in terms of the local basis, right? And so it must look something like this, where these things gamma, I, j, k are called the Christoffel symbols and are uniquely determined smooth functions. Okay. And well, they are important. I don't know if they are very important or not, but they are at least interesting because most of the important invariants of Riemannian geometry can be locally expressed in terms of Christoffel symbols. Okay. So, and knowing this, since the function since the connection is linear in the first entry and C-infinite linear in the first entry and has this Leibniz rule in the second entry, we can locally express the connection evaluated in two vector fields like this, right? So yeah. Here I'm just writing y in terms of the local coordinates. Here I'm using the Leibniz rule. And here I'm just changing, I'm using this idea of introducing the Christoffel symbols and then just changing the domain index so that I can put everything together. And well, I don't know if you appreciate it because perhaps I explained it very fast, but here there is a very nice example of why using Einstein notation might make things much simpler, because I think this is a particular place where using the sigma things makes it really confusing. But yeah, I don't know if you agree with me, but okay.
Yeah, I don't know. I'm kind of from the very first time I saw it, I'm kind of very prejudiced against Einstein's notation. But yeah, okay.
Yeah, the thing that I do not like is that you are forced, at least here, you are forced to put this some I don't know how to say this in English.
Yeah, the summation. Yeah.
Yeah, the summation inside of another one, and it's a little bit hard to go around that if you want it to look nice.
Okay. But just a question. But don't you like at some point get confused because if you omit the summation symbol for k, let's say there, isn't there ever a point where that gets you confused?
Yeah, if you do not know that you are using the notation, but
okay,
as long as you know it, it should not be confusing, because that's the reason for which you use indices on top and indices on bottom, right? That's the way to know that you are summing over something.
Okay.
But yeah, it can be confusing. I agree with that. That's the reason for which I do not like it. But I think that in this particular case, the formula looks a little bit nicer, at least. Okay. So now a proposition that I should mention, but that I do not want to go much deeper into, is that every manifold M possesses a connection, right? And the proof is not that hard. One can define a connection, one can fix an atlas for the manifold, and one can define like local connections, and then one can paste them using partitions of unity. But the thing is that an arbitrary connection is not might not be that interesting, right? Because we are not sure that it represents everything that we want to be represented by a connection. So we'll eventually arrive to a connection that actually seems to represent something that we like. That is the Levi-Civita connection.
Yeah. So one question. So for instance, Rn.
Yeah.
Does it have like many connections different from the usual one? Do you know?
I'm not exactly sure, but I know that one can give almost arbitrary values to the Christoffel symbols, and that they will determine a connection. Because essentially you're trying to solve a system of linear differential equations, right? So yeah, I think you can give arbitrary values to the Christoffel symbols, and you should be able to find a connection that satisfies that. I'm not sure, but I know where to read, so maybe tomorrow I can answer with a little bit more detail.
Okay.
Okay. Now, so yeah, we still have in mind, we still want to solve this problem or give a way of identifying tangent spaces, right? So what we want to do is introduce parallel transport, even though we actually already solved the original problem of differentiating vector fields in the direction of other vector fields. So for that, we introduce covariant derivatives. That is a way of calculating how a vector field changes along a curve, right? So we want to have a smooth manifold, we want to have a connection on that manifold, and we want gamma to be a smooth curve. Then there is a unique R-linear map that I denote by dt, defined on the vector space of smooth vector fields along X along gamma, which satisfies the following conditions. So vector fields, smooth vector fields along a curve are a little not exact, not that. Yeah, it is not completely obvious to decide what that means. Essentially, the idea is that you have a function from I'm sorry, I just forgot what I wanted to say. Yeah, but you have to have a function that goes to the tangent.
Yeah, the tangent
manifold, tangent bundle, and so that when you project, you stay in each point, right? But I just got a little bit confused. I'm sorry.
No, it's fine. But so here the interval AB, then is it the same interval of definition of the curve gamma?
Yeah, it is. Okay. I should have written that. Yeah, gamma is defined in an interval AB, and actually, for gamma to be smooth, one requires that the curve can be defined in an open interval a little bit bigger than AB. Okay, but for most things, it is very convenient that the interval of definition is compact. So that's the reason for which normally one takes compact things. And okay, so we want to prove that there is a unique R-linear map that satisfies these two conditions, right? The first one is that if we take any smooth function that defined on the interval to the reals, then our covariant derivative satisfies a Leibniz type rule. And second, that if the smooth vector field defined in the curve along the curve gamma is induced by a vector field defined in the whole manifold. That is exactly this that is written here. And then for every point in the interval, one can calculate the covariant derivative of the vector field X at that point by evaluating the connection or by differentiating zeta in the direction of the derivative of gamma at the point t0, and evaluating all that in gamma of t0, right? So here we are using that idea where we do not need to have a globally defined vector field in which direction to differentiate. We only need to have a fixed direction. Because I mean, there is no reason for which we should be able to extend the vector field given by differentiating gamma to a vector field defined at least in an open set of the manifold, right? Okay. Now, the idea of the proof is simple. We reduce the problem to showing that the problem can be solved in a chart, I mean. Okay, so for that.
So just one question. So
yeah.
Sorry to interrupt. So when you write dt of x, I mean the t, that t makes reference to kind of to a t in the interval, right?
Yeah, not really. It just makes reference to the fact that we are differentiating with respect to this with respect to the variable time, right?
Okay, but so it's kind of an abuse of notation somehow, like a
yeah.
Somehow?
This, for example, is an abuse of notation. Let me see. This is an abuse of no. Yeah, this is an abuse of
the one on the left.
Yeah, and it's exactly this same abuse of notation here, right? I mean, it's not the same concept, but it is the same idea. Okay. Actually, some people, for that reason, normally write dt of x evaluated at s, for example, where there is no abuse of notation, right?
Okay.
So the first thing is that
sorry, I have another question. I'm sorry. So are we like pulling back x through the curve gamma, or why is it defined as why is the vector field x also dependent on the parameter t?
Yeah, so that's the reason for which I was saying that one should be a little bit careful with defining smooth vector fields. So a smooth vector field along a curve should be a function that goes from the interval where the curve is defined, a smooth function that goes from the interval where the curve is defined to the tangent bundle of the manifold. And so that when you project from the tangent bundle to the manifold, I mean, x of t is located in the tangent space of gamma t, right? So yeah,
perfect. Thank you.
Yeah. Okay, so now since we want to reduce the problem to working at a chart or at an open set covered by a chart, we can observe first that the value of dt of x at a point t0 depends only on the value of x in any interval around t0. And to prove this, one would use a similar argument to the one used in the first proposition I proved. Because of this property here, one can do that. Once one knows that, we can say, okay, we'll work in a local chart. We can choose local coordinates, and we fixed a t0 and we choose local charts, local coordinates around the point gamma of t0. And since this is a smooth function, we can write it locally like this, right?
Sorry, just one more thing. On the other hand, it does depend on the parameterization. It does depend on the parameterization of gamma, right? I mean, d of x does depend on the parameterization of gamma, right? I mean, in other words, let's say that you take an orientation self-homeomorphism of the interval AB, even like a class C infinity. The original connection would not be necessarily be the same as the final one, right? I mean, let's forget about what I just said, because kind of in your definition of covariant derivative, you say that if x is a vector field defining the whole, if x comes from a vector field defining the whole manifold, then the value of the covariant derivative at x is determined by the value of the connection at the gamma prime of t, right?
Yeah.
So this makes that covariant derivative dependent on the parameterization of gamma, right?
Not really, because it depends on what you mean by parameterization. But yeah, I mean, two curves that have the same image do not necessarily induce the same covariant derivative.
Right, exactly. That's what I'm saying. Yeah.
Yeah. That's completely
true. Okay.
I mean, I don't know if they do induce it, but at least a priori they should not induce the same covariant derivative. Okay, now, so we can write the vector field along the curve like this in local coordinates, where these functions are smooth, and these are the vector fields induced by the local coordinates restricted to the curve. So they are obviously extendable since we are just restricting the coordinate vector fields to the curve. So that's it. That it will be important eventually. Yeah, so here is where we use that the coordinate vector fields restricted to the curve are obviously extendable, because then we can evaluate the covariant derivative of x at a point t by this formula, right? Where we are using, I mean, we are supposing that this function exists and that it should satisfy these two conditions. So here we use that it satisfies the first condition. We are actually using that it satisfies the two conditions, right? I mean, we first use the Leibniz rule, and then we will obtain this second term. I mean, a sum of second terms, and there we substitute the covariant derivative by the connection, right? And then we arrange things and we arrive at this. Yeah, I mean, here we are using, once again, that the connection is determined by the Christoffel symbols. And we are using that gamma prime looks a certain way in local coordinates, right? So gamma prime is simply differentiating each of the, I mean, gamma prime in local coordinates is gamma in local coordinates. Yeah, you look at gamma in local coordinates and then you differentiate with respect to time, and that's gamma prime. Okay, and we use that to arrive at this. And then since we have a fixed connection, that means that we have fixed Christoffel symbols. And so if the map exists, it should be unique because it is determined by this expression, at least at a particular chart, right? At a particular open neighborhood that is covered by a chart. So, yeah, that's what I say here. No? If if the image of gamma if the image by gamma of the interval is contained in a single chart, we can define this function by the above equation. And in the general case, we simply cover the image of gamma by coordinate charts and define the function locally, and by since it must be unique since the function must be unique in each of the charts, then in the overlaps it will coincide and it is well defined, right? So yeah, that's mostly it. I don't know if there's anything else I want to say. Okay, and now we are ready to define parallel transport, right? Yeah, it would have been nice to put some pictures here, but I didn't take that into account because the thing about parallel transport is that what we want to do is take a curve in the surface, take a vector field, and move. Take a point, take a vector, a tangent vector at that point, and move that vector along the curve as if it was not changing, right? As if it was exactly the same vector, just translated. But of course, that idea of being the same vector depends on a lot of things, right? So for us, what it will mean for a vector, for a vector to be the same vector will be that the vector field is parallel, right? So that means that when you differentiate that vector field, when you covariantly differentiate that vector field along that curve, it is always 0, right? So that the covariant derivative defined by that curve doesn't notice that the vector changes, would be like what I would try to interpret it as. And well, yeah. So using ordinary differential equations, one can prove the following. I'll give the details in a moment. So if we have, once again, a smooth manifold, connection on the manifold, and a smooth curve, then if we fix a point in the interval, oh, sorry, here I made a mistake. I should have put T0 here too. And we fix a vector field, a vector tangent to gamma at the point tangent to M at the point gamma evaluated at T0, then there is a unique parallel vector field X along gamma such that at T0 the vector field has a value B. So once again, it suffices to prove the result in the case in which the image of gamma is contained in a single coordinate chart, because once again, one can use uniqueness to paste things together if we have several coordinate charts. Okay, so if we are working in a single coordinate chart, one can express the vector field along the curve gamma, once again as this. And from the previous proposition, we know that the covariant derivative in local coordinates should look like this. And we want this to be 0, so that the vector field is actually parallel. And that induces a system of n linear ordinary differential equations that are the following ones. Yeah, that what I'm saying is that this happens if and only the following linear system of n differential equations has a solution. That's this one. That's given by the coefficient of each vector field, right? And this makes sense because the vector fields are linearly independent. The coordinate vector fields are linearly independent. So we want this to have a solution. And since the system is linear, we know that it has a unique solution given a particular initial condition, where the initial condition is determined by this value, and that the solution will be defined for every point in the interval where we are working. And that proves the theorem, right? Because we said it is enough to work in a single coordinate chart, and then we saw that in a single coordinate chart, the problem has a solution. Okay, so yeah. And now this allows us to define parallel transport along a curve, right? Because we can once again look at a smooth manifold, fix a connection, take a curve in the manifold, and then we define the parallel transport from the point gamma A to gamma T along gamma as the linear map. I'll explain in a bit why the map should be linear. That goes from the tangent space to gamma A in M to gamma T in M, which associates to a particular tangent vector at gamma A, the vector which we just, yeah. To V, we associate the evaluation at T of the vector field, of the parallel vector field whose existence we weren't guaranteed in the previous proposition, right? Okay, yeah, and well, what happens is that this is actually a linear isomorphism, right? And the reason it is linear is because the initial conditions determine the solution, right? Well, because of that, and because the covariant derivative is linear, right? Because if we say, I think I'd like to write something. Just give me a second. Can I write using this or not?
I'm not sure, or I don't know if you can write there, or maybe you can switch to a board, right?
Yeah, I'll do that because it seems that I cannot write here. Just give me a second. I'll stop sharing for a moment. Yeah, the thing is that I haven't found a board that I actually find nice enough. So that's the reason for which I do not love using boards. Oh, but I can use the Zoom board. Okay. Yeah. Okay, so we have.
Just sorry, before you start, because you're going to speak about this linearity, right?
Yeah.
Yeah. So can you say that it's because the system of linear equations kind of because it's linear, and then the you know the solution.
Yeah, the solution space
Right.
is linear.
Yeah. I guess. Yeah, it's kind of you change. Yeah, kind of you change the initial. No, I guess it's you, because what you do is kind of you change the initial conditions, right? Kind of No, yeah. That's it, right? I think that's it. Take the system of linear equations without initial conditions, and take the whole solution space. It's a vector subspace, right?
Yep.
And I think that's it, right? And then the rest is kind of just play with the uniqueness, and then take a sum of two vectors.
Yeah,
right?
that's exactly what I was
Right.
going to say. Not exactly.
Okay.
But yeah.
Okay. You can say it if you want. Yeah, as you prefer.
I don't know. Would you like me to say more about that, Javi, or is it fine?
No, it's completely clear. Thank you.
Okay, and then okay, you're back. Okay, and then
Well, nice board.
We should also talk about why is this this linear function an isomorphism, right? And
right.
And it is an isomorphism because of uniqueness, right? It is injective because of uniqueness, and since the dimension of both tangent spaces is the same, injective. If the function is injective, it is surjective, and then it is an isomorphism, and that's what we wanted to prove. So yeah, we finally arrived at a not really canonical way of identifying tangent spaces, right? Yeah, because this depends on a lot of things. We chose a connection, and we chose a curve, right? At least it depends on those two things. And we still have no preferred connection. Well, we will have one tomorrow. Yeah, I think that I would like to leave it here.
Yeah. Okay. All right. Okay. Thanks. And then what do you plan to do tomorrow?
I will talk about the Levi-Civita connection. Riemannian connections in general, and talk about if we also ask for the connection to be symmetric, then we have a unique connection. And hopefully I should also be able to talk about curvature, but I'm not sure because how much time did I take today?
Like 50 minutes, something like that. Maybe 55 minutes, something like that.
Yeah, then I should have it should not take me more than 1 hour and a half, I think. Because, okay. Yeah, I think this is the part that is, I'm not sure.
Yeah, no, okay, no, it's fine. Yeah, okay.
Yeah.
All right, then, yeah, thanks. Then I'll see you then tomorrow.
Yeah.
Okay. All right, yeah.
Thank you, Carlos. Goodbye.